In this section, I want to introduce or emphasize 3 key issues that will frequently come up in ordering games that involve more variables than the number of slots. And those are, first, the importance of directly representing into your main diagram numbers-related issues or numbers-related rules, like this first one. The second issue is how we handle must-be-together rules, like this second one telling me that these 2 variables, O and P, have to be together. And the third issue is how we handle certain relative order rules now that you're allowed to have 2 letters in the same slot, now that you're allowed to have ties in the game. In particular, how do we handle a negative relative order rule like this? We have to be very careful when it's possible to have ties in the game. But first, let's go ahead and start with our setup. We have 6 animals being placed into 4 different cages from 1 through 4. Each animal will be housed in exactly 1 cage. So that means these 6 animals, they're each going to appear once in our game. Now notice that this first rule here is telling me each cage will have exactly 1 or 2 of these animals. So how do we handle that issue in our main diagram? Well, first of all, I'll draw 4 cages from 1 through 4. And since I want to visually represent that each cage will have either 1 or 2 letters assigned to it, here's one way to do that. I can draw a second row of slots and then put parentheses around them to indicate that they don't necessarily have to be filled. To me, this visually means that this bottom row does have to be filled with at least 1 of these animals because there's no parentheses around it. But I can also put 2 animals in some of these cages, and the fact that I didn't draw another row above is telling me that there's a maximum of just 2 per cage. So that's one way to visually represent the idea of a maximum of 2 per cage, but a minimum of 1 per cage. Now there are other ways to handle this kind of rule. Sometimes people will just write each cage will have 1 or 2, and writing this near the diagram will be enough to remind them of the constraint. Sometimes I'll choose to do that, but I'll usually prefer to draw the slots directly with parentheses. And sometimes I may even write both this representation as well as saying there's a maximum of 2 per cage and a minimum of 1. What I'm trying to emphasize here is that it is incredibly important that you not forget about this kind of rule and that you do whatever you can to visually represent that in a way that you're not going to forget it. So next I'll go ahead and write my 6 variables L, M, O, P, Q, R. They're each going to go exactly 1 time. And now we'll turn to the rules. The first rule is the one we talked about at length. And since we've already represented it over here, I wouldn't feel the need to write it in my list of rules. But just so we emphasize the importance of this rule, I'll go ahead and represent it like this. I'll use the number symbol here to indicate it's a rule about numbers, and I'll put the content of that rule over here. Each cage gets 1 or 2. The next rule is telling me that the ostrich has to be in the same cage as the python. So this is a must-be-together relationship, and I want to make sure I represent this visually. What is it going to look like if O and P are in the same cage? Well, that means they're going to be vertically in the same cage. So that's why I'll represent this like a vertical block. O and P are always going to look like this when I put them into my diagram. Now you could add a switch to it like this if you wanted, but it doesn't really matter who's on top or who's below. And I'll just naturally be reading this OP block as if it were switchable. The third rule says the P is lower numbered than the R. So that means P has to appear to the left of the R. I'll diagram that like this. Of course, you could just directly put it onto rule number 2 like that, but I'll go ahead and do that later. Now you have to be really careful with the fourth rule here, which says that the mole is not housed in a cage numbered lower than the cage in which the quail is housed. So the mole cannot be lower numbered than Q. That means the M is never going to appear to the left of Q. Now, if this were a game where you only had 1 letter per number, 1 letter per cage, then that would mean if M is not before Q, that the M has to come after Q. But because this is a game where you can assign more than 1 letter to each of these cages, Q before M is not entirely capturing what this rule means. Because sure, this is one way that the M is not lower numbered than the Q, that the M is not to the left of Q. But there's another way that the M could not be lower than the Q. And that is if they're in the same group, if they're in the same cage. So to represent what this rule really means, I actually like to draw out both of the possibilities. Either Q is before M, or Q and M are together in the same cage. So I actually have two options for this rule. So that's how I'll diagram it over here. And the final rule says the Q is higher numbered than the L, so that's going to look like this. So now let's go ahead and make connections between our rules. So let's take a look at the rules that mention the same letter that visually look like we can connect them. And we can start with rules 2 and 3, which both mention the P. So O and P have to go together, and since the P has to come before the R, that means the OP vertical block has to come before R. Now we can take a look at rules 4 and 5, and you can see that we have two options for rule 4. But since L always has to go before Q, you can just combine this L before Q with both of the parts of the OR. For example, you could have the L before Q before M like this, and that's if you're in this version of rule 4. Or you could have L before the vertical QM like this. And that's how I'll represent the combination of rules 4 and 5. So right now, rules 2 through 5 are already handled. We've already combined them over here. There's just one more rule I want to think about, which is our numerical rule. Remember, that said every cage has to have 1 or 2 animals. And at this point, because we have a rule about the numbers within each of the cages, I want to think about the distribution of these 6 animals into these 4 cages. Now this is totally something we could have done at the start of the game, but generally I like to wait to think about the distribution until after going through the rules, because sometimes you get to a rule that will impact the distribution. So to figure out the distributions of animals to cages, I'll start by maximizing the number that I can put in any one cage, and that's going to be 2. And then I'll maximize the number I can put in another cage, that's going to be 2. So far I have 4 animals distributed among 2 cages. That means I have 2 more animals left for the remaining 2 cages. That means those other cages will have to get 1. Now this adds up to 6 animals, and it complies with the constraint of each cage having 1 or 2 animals. Now there's no other distribution here, because if you tried to subtract 1 from this 2 and add it over here, well that's just the same 2, 2, 1, 1 distribution. At all times, 2 of these cages are going to have 2 animals, 2 of these cages are going to have just 1 animal, although I don't know which number is going to be in which particular cage just yet. Now we're ready for a challenge question. Go ahead and try this on your own, and we'll discuss when you're back. The condition here is if cages 1 and 2 each have exactly 1 animal. And the question is, what is the complete assignment of animals to cages in that case? So if cages 1 and 2 each have exactly 1 animal, here's what I want to do on my scratch paper. I'll start by drawing out my slots, but I want to make sure I represent the idea that cage 1 and 2 are only going to get 1 animal. So that means they don't get to fill this slot. As I said before, it's really important to visually represent numerical constraints like this, because if you forget that kind of constraint at any moment, that's what leads to problems taking much longer. Now, by the way, another way that I like to represent that I can't add any more to particular groups is by sealing off the group like this. Visually, it looks like I'm capping the group. I can't go beyond this cap. And sometimes you don't need to draw anything like that. If you just know that you only have 6 letters and you draw out the 6 slots like this, that can often be enough to tell you that cages 1 and 2 only get 1 animal. So again, it doesn't really matter how you represent the constraint, as long as you are going to understand the impact of these numbers rules. So what's the next step once we have sealed off groups 1 and 2? Well, we still have to put down the OP vertical block before R, and we still have a choice of which of these LQM relationships we're in. Let me start with the OPR. I'm going to start by trying to see what's the furthest to the right that I could put this OP. Well, the OP is not going to be able to go in 4, because then I need room for the R after it, and if OP were in 4, then there's no room for that R. So that means the OP has to go in 3, and the R will have to come after it in 4. And now let's take a look at our other rule. Which version are we in? Well, let's see. If we're in the LQM version of this rule, then that means the L, Q, and M would go like this. But if we're in this version of the rule, it turns out that's not going to work because I have nowhere to put a vertical QM block right now. None of these cages right now is going to have 2 open slots. So that means we are not going to be in this version of the rule. We must be in L before Q before M, and that's why this is what the arrangement will look like. Here's another question for you. Go ahead and try this on your own. The condition is if R is alone in cage 3, what's a complete and accurate list of the letters that must be assigned to cage 4? So again, our condition has this numerical aspect to it. R is alone. That means R is the only one in cage 3. So I want to start by drawing my set of slots. I want to put R in 3, but to represent the fact that R is alone, let me just go ahead and seal cage 3 off. Again, if you fail to represent these numerical aspects of these constraints, that's going to lead to so many mistakes and it's going to take a lot more time. And I'll still go ahead and put parentheses around this top row because I don't yet know which of these cages is going to have more than one animal. But now I'll go to my rules. I still have to put down the OP vertical block before R. And so it looks like I have two options for the OP vertical block. Let me just go ahead and try both of them. One possibility is the OP block goes like this, and the other possibility is the OP block will go like this. And again, I'll seal off the R. So now what is the next step? Well, I'll look at the only other rule remaining. It's either L before Q before M, or the L is before a vertical QM. Now, in the first possibility, there's no way I can fit L before Q before M, because I only have cage 2 and cage 4 open. So that means I have to be in this version of the LQM relationship, and that means the L will have to go here, the QM will have to go like this, and now cage 2 has only L, because I placed all the animals. If OP is going in the second cage, again, I don't have any room to put LQM in separate cages, so I have to put the L in one, the QM will have to go after it, like this, and the L is alone in cage 1. So it turns out the Q and the M always have to be assigned to cage 4.